Okay, so last class I asked this question: what is the probability of cool with union of smart, union hardworking? Right? And we had some discussion about, like, what do we need to do with that middle term? Do we add it in once? Do we subtract it once? Do we add it in 3 times? So I said, for extra credit, you could send me your answers. So people sent me answers. I haven't responded to any of the emails because I didn't want you guys to like tell each other, like, oh, I got it right, so you send this answer in too. Anyway, so the correct answer, let's draw these out. So if we want probability cool, union smart, union hard, we know that the first part is probability cool, right? So probability cool, how am I going to draw that? There's probability cool. That's not good enough. Christian for working. Well, I'll just do this. There we go. So there's probability cool, right? Plus probability smart. Now, when we add in the probability of smart, now we have 2 of these, right? There's overlap, because we had this already from cool, and now we have it again from smart, so there's overlap there. So let's subtract that out right now, okay? Minus probability of cool intersection smart. Right? When we subtract that out, now we don't have any more overlap. Right? Everything's good. Okay, so we've got that. Now we also want to add in probability hardware. Okay, so we add this in. Now, what do we have? Well, now we have a lot of overlap, right? All that indicates duplicated information. And we need to get rid of that, right? So, one thing that we can do is we can subtract out the probability of smart and hard. Sorry, intersection hard. And if we do that, we'll only have overlap right here, right? So we need to get rid of this overlap. So if someone would have said, like, okay, let's just minus probability business, I would accept that. That's true. You subtract the probability business, and you're finished. If, however, you said something like, let's subtract out the intersection of cool and hardworking, minus P cool, well, that gets rid of this, but now we're like negative, right? We're negative this part. So we took that, we didn't have this to take away, but we took it away anyway. So what do we need to do? We need to add it back in. How many times? Just 1. We just need to add it back in once. So the final term would be P cool, intersection smart, intersection hard. That's it. When we add that back in, we aren't missing that anymore. We have everything. I don't think anyone sent me the emails. I didn't check all of them because some people sent me them like late last night. I wasn't looking at them anymore. Did anyone say 1? You sent me an email with 1? That's correct! 1 is correct. Awesome. That wasn't what I was looking for, but that's correct the way that I define the Venn diagrams, right? There's no bounding rectangle in this. And I said if there's no bounding rectangle, then the total surface area for these things represents all of the outcome space, which represents probability of 1. So, congratulations. 1 gets the extra credit as well. Does that make sense? Any questions on it? Okay, let's talk about hypothesis testing. Last time, wasn't so happy with the way things went, so let's try it again from a different angle. All right, is this coin fair? Yes. You don't know. We don't know, right? It might be fair, it might not be fair, right? So if we ask if this coin is fair, this is a research question. You can do research on this to figure out what the answer is. Now, how do we answer this question? How do we do our research? We make an experiments. We can do simple statistical experiments, right? We start flipping the coin. All right, so to answer, we're going to just flip the coin. This is a statistical experiment. Now let's flip the coin once, all right? Let's see if I can do it. What is it? It's tails. Okay. I was not clairvoyant, so I got the answer wrong. Imagine it was heads. Now, if it was heads, does that mean that the coin is fair? It was tails. Does that mean that the coin is fair?
No.
Why not?
You don't have enough. You don't have proof.
We don't have enough proof.
Yeah.
I don't like the word proof, right?
Everything.
So we don't have enough evidence, right? We don't have enough evidence. We have one coin flip to go off of. Now, if that's all of the evidence we have, we might conclude that the coin wasn't fair. But really, that's really bad evidence. So imagine we got heads, and we asked the question if it's fair. Now, if we assume it is fair, right? Let's assume that this coin is fair. We don't really have a good reason to assume that this coin is biased. So when you answered it was fair, like, that's what most people would assume, right? The coin is probably fair. All right, so if we assume that it is, we can calculate the probability of observing what we observed, right? So what do we need to calculate the probability? What do we need to calculate the probability of getting one heads if it was fair? We need the probability of getting heads for what? For this coin? But we don't know what the probability of getting heads for this coin is, right? For a fair coin, right? We need the probability of heads for a fair coin. We also need to know how many times we flipped it, right? I mean, if we flipped the coin 1,000,000 times and got one heads, that's way different than if we got one heads in one flip, right? So we need to know the probability of getting a heads if it's a fair coin. We need to know the total number of flips, and we need to know the number of flips in which we observe heads. So what are these things? 0.5 for a fair coin. 1. 1, if I had really gotten the heads, okay? These are called parameters. So the probability of getting the heads for a fair coin and the total number of flips is a parameter. So what is a parameter? What did I say last time? You guys remember? It's like a value that describes how something works, right? If we know the probability of heads and we know the total number of flips, we know how this probability function should work. We can calculate the probabilities for these things, right? This last thing, the number of flips that we observe heads, this is a statistic. What type of statistic is it? Is it a descriptive or an inferential statistic? It's a descriptive statistic. That's exactly right. Now, we're going to use our descriptive statistic in addition to the parameters and create an inferential statistic from that. Okay, so the probability of an event. This is a product of the probability of the observed outcomes. This is from Monday's class, right? So what do we need in order to calculate this? We need to calculate, or we need the probability for each outcome that we observe, and we need the number of times that we observed each outcome. So the probability for each outcome, we didn't observe tails, but the probability of heads and the probability of tails, they're both 0.5 for a fair coin, right? How many times did we observe heads in one flip for this example? 1. How many times did we observe tails?
None.
None, right? We observed heads once, we observed tails 0 times. Again, these are our parameters. And we got these from our assumptions. We got this from theory. Our theory about what a fair coin is. Okay, so the probability of the event heads. So I've got these curly brackets on there. So I use this to indicate the particular set of outcomes that we had, right? We had one flip, so our set of outcomes was just one head, right? So this is our set of outcomes, and this is equal to the probability of heads raised to the number of heads that we got, times the probability of tails raised to the number of tails that we got. You guys remember that? So all this is 0.5 times 1. 1, where did I get the 1 from?
Because of the 0.
Yeah, because of the 0. So probability of tails, this is 0.5, right? So 0.5 to the 0th power is 1. Any number to the 0th power is 1. So we have 0.5 to the 1, which is 0.5, times 0.5 to the 0, which is 1. So 0.5 times 1 is 0.5. So is the coin fair? The probability that we would observe this set of outcomes, that is one head and one flip, is 0.5, right? So is this good evidence that the coin is fair or not fair?
Yeah.
That
Because
what?
it's equal. The heads and tails are equal because of its is 0.5.
So the probability of this was 0.5 when the probability of a fair coin turning up heads is 0.5, right? But the question we want to answer is this coin fair? People earlier said we don't know. And I said, why don't we know after one flip? And someone said, because we don't have proof, right? I said I didn't like the word proof. What else did I say we should say instead? We don't have evidence, right? So, even though all of our observations were heads, there's a really high probability of getting a set of outcomes like this, right? 50% of the time, we're going to see a set of outcomes like that, right? So, the probability of event H is really high if the coin is fair, right? So this is not very convincing evidence that the coin is not fair, right? So, how about getting 5 heads and 5 flips? If I did that, I could actually maybe get a head. Oh, tails. If I did this 5 times and I got 5 heads, right? What would the probability of this set be, right? A head on the first, a head on the second, a head on the third, a head on the fourth, a head on the fifth. What's that probability?
0.5 to 5.
0.5 raised to the 5th times 0.5 raised to the 0th, right? Because we have no tails. And that is roughly equal to 0.031. Now, how is this? If I flipped the coin 5 times and I got 5 heads, is this more convincing evidence that the coin is not fair? I would argue that we do know. I would argue that we don't know whether the coin is fair or not, but I would argue that we do know whether the evidence is more convincing. All right, let's take it to an extreme case. Imagine that we flipped the coin 1,000,000 times, and every single time we flipped it, we got a head, right? What would the probability of observing that be? It would be really, 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 really low, right? Would that be fairly convincing evidence that the coin is not fair? Yeah. So we can potentially, maybe, we can look at the probability of the set of events to get an idea about whether or not the coin is fair. So before, the probability of this event was really high. So we said, okay, we don't have enough evidence. We don't know if it's fair or not. It's not really conclusive, right? Here, now, the probability of this is pretty low, right? So this is better evidence. Not conclusive evidence by any manner, but better evidence. Does that make sense? Now, so we might be more convinced that the coin is not fair. How about this? The probability of 10 heads in a row. The probability of this event. Heads, 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 heads. the 10 times 0.5 to the 0, and that equals this. So a 1 here would be 1 in 10, 1 in 100, 1 in 1,000. So we have almost a 1 in 1,000 chance out of every 1,000 times that we do 10 flips, we should only see something like this once, basically, right? How's that for evidence?
Wow.
So that's really low evidence, it's bad evidence? Like when I think of evidence, I think of like low meaning weak, it's weak evidence. It's weak evidence. Really? So let me ask a different question. Is this evidence weaker than the evidence that we saw before?
Yeah.
It is. Okay, I'm wondering if this is like a native English speaking thing. This is actually much, much stronger evidence. When the probability is low, right? That means it's very unlikely to have happened just due to chance, right? So the probability of low, this is very unlikely to have happened just due to chance, which means that it's pretty strong evidence, right? When the probability was high, that means that it was very probable that we would see something like that just due to chance. So that was weak evidence, right? Does that make sense for everyone? So you might not say this is strong enough for you. Maybe you want to do more flips. That's totally up to you. But comparing 10 flips to 5 flips, this evidence is much stronger than getting 5 heads in a row, which was much stronger than getting 1 head in 1 flip. Do you have a question? All right, so the probability of this event is very, very low if the coin is fair. So this seems on its face like the coin is not fair, right? So maybe we could say if the probability of an event is low, then the coin probably isn't fair. Does that seem reasonable? Okay, actually, what's the probability of this event? You see that logic doesn't work very well.
Same.
The probability of this event is exactly the same as the probability of that event, right? So how do we calculate the probability for this event?
0.5
0.5 to the 5th
multiplies
times
of
0.5 to the 5th. And that's exactly the same answer we got up here, right? So the probability of observing this event is really, really low. The probability of observing this event is also really, really low. But if the coin is fair, we would expect to observe events like this a lot, right? So maybe we don't want to make a decision only based on the probability of an event, okay? All right, so if we want to conclude whether a coin is fair or not, we should not base our decision on the probability of the observed event. So if we're not going to use the probability of an observed event to figure out whether the coin is fair or not, what else could we use? I already sort of gave away one potential answer. Well, we know the null hypothesis, right? We assume that the coin was fair, and from that we said that p heads for fair coin is 0.5, and p tails is also 0.5, right? So if we aren't going to use the probability of the observed event, maybe we could use something else. Maybe we could use our make our decision on the probability of events like the one we observed, right? So instead of the probability of this event, or the probability of this event, we would look at the probability of events like these, of any event where we have 10 heads, or of any event where we have 5 heads. Does that make sense? So, how do we do this? Well, what do we need to calculate this? We talked about this on Monday. In order to calculate the probability of a set of events that are all like one particular event, what do we need to do? It's not a permutation, but it's close. It's a combination, right? So we need to do a combination problem, right? The combination will tell us how many events are like the one that we observed, right? So we can do a combination to figure out how many events are like the one that we observed, and then what do? We need one more piece of information. Probabilities range between like 0 and 1, right? So if we have just the number of times that we observe events like that, say what?
It's less than 5.
If what's less than 5?
The answer of the combination is less than 5, then it's is it how we measure?
P-value.
No, not p-value yet. We'll get to the p-value. But to calculate this probability, we need to know the number of events that we have, like the one we observed. What else do we need to know?
Null.
We know that already. We do need to know that, but we already know that. Since we know that, what can we calculate? We know what the null hypothesis is. We know how many times we observed heads, right? So what can we do? We need to calculate the probability for the event that we observed, right? So if we have the probability of the event that we observed, and we know the number of events that can happen like the one that we observed, we can multiply that probability times the number of events, right? Because the events are mutually exclusive, right? Getting the first 5 heads out of 10 flips is different than getting the last 5 heads in 10 flips. The probabilities for each of those is the same thing, so we can add up those individual probabilities, right? So we need the probabilities for each outcome that we observe. Those are our parameters, the number of times that we observed each outcome. Those are our statistics. So the probability of events like ours, events like the one that we observed, is just the probability of our event, which we calculated here, right? Times the number of events that we have that are like ours, right? So this is just what we did before, the probability of heads raised to the number of heads that we get, times the probability of tails, times the number of, or not times, raised to the power of the number of tails that we got, right? That's this first part. This last part, what's that again? It's not a permutation. It's a combination. So what's the formula that we should use for the combination?
Factorial.
N factorial.
R factorial.
R factorial.
And minus R.
N minus R factorial. Right? So for our example, like what would this be when we got 5 heads in 5 flips? I'm sorry, 5 heads in 10 flips. What's N? For 10 flips, N would be 10. What's R? 5. Right? Root. So that's just the combination. Sweet. So now we can calculate the probability of events like the one that we observed. Right? You saw that just using the probability of an event is not a good way to make a decision. So maybe the probability of events like ours, maybe this is going to be a better way to make a decision. Okay? So imagine we get 10 heads and 10 flips. So I'm using the conditional probability here. It's the probability of 10 heads given 10 flips, right? Okay, so the probability of 10 heads and 10 flips, what should this be?
1.
1 to the 7. 1 to the 7. 1 to the 1,000. 1 out of 12.
Say it louder.
No, 001.
Yeah. Okay. What else? How'd you get that?
Because there is no other combination that you can get other candidates in 10 flips. That's only one. The probability is one.
So he's basically got the right answer. So if we don't just go straight to the answer, but instead try to figure out what the answer is, right? Let's use our equation that we had. So what's the equation?
Our event
Our event, okay.
multiplied by the combination of like our events.
Probability of our event times number events
Like ours.
like ours. And the probability of our event, what is this?
Like 001.
Okay, 0.001. How did you get that? He's a genius.
We have it from previously.
Yeah, we actually do have it from previously, right? So if we go back, we see that he doesn't have, you know, an amazing math skill. Well, maybe he does. I don't know. We can do some more tests to find out. I guess he has a really good memory. But yeah, so that's basically it. So what we had, if we were going to calculate this instead, you know, just put it up here, boom, that, right? This was the 0.001 that we calculated earlier. And this, well, those cancel out, so we're just left with 1. 0.001 times 1 is that. It should actually be squiggles, because it's really 0.009 something. Right? Okay, so awesome. So the probability of events like this, right? Not the probability of this event, but the probability of events like this is really low. So this seems very convincing that the coin is not fair. So is it? Well, let's look at the event that we would expect most often, which is what? If we flip the coin 10 times, what type of event should we see more than anything else? We should see heads how many times? No. 5, right? The thing that we should see most often would be 5 heads, right? So the probability of 5 heads in 10 flips, well, it's just probability of heads to the 5th times probability of tails to the 5th times this, right? 10 factorial over 5 factorial times 10 minus 5 factorial. And the probability of that is approximately 0.24. So 1 out of every 4 times almost, we would see an event like this, right? If the coin really was fair. That's a pretty high probability, right? The probability is a 1 in 4 chance we'll see something like that. So if we saw something like this, we might say, aha, this seems like fairly convincing evidence that the coin is fair, right? Because we would see that a lot if it was fair. But the probability of this occurring is very low if the coin really was fair, right? So this seems like a much better decision rule than what we were using previously. Does that make sense to everybody? Now, we have a problem. And that is when you have a large sample size, even the most probable event will have a low probability for events like that, right? So if you flip the coin 1,000,000 times, the most probable event would be 500,000 heads, right? But the probability of observing 500,000 heads in 1,000,000 flips is really low. So let's not do the 1,000,000, let's just do 1,000. So the probability of 500 heads in 1,000 flips. How do we do this? Now we can see if he's really a math genius. Give me the answer. You can't. Can you tell me how you could figure this out?
I mean, the same rule. We have the our events.
Okay?
The our events multiplied by 1,000 factorial to the
So we have part of it is 1,000 factorial.
to the 500 multiplied by 500 factorial.
Not to the 500, but divided by 500 factorial.
Multiplied by 500 factorial. And
So this will tell us the number of ways that we can get 500 heads, right? So we're going to multiply the number of ways that we can get 500 heads by the probability of any one example of 500 heads, right? So what's the probability of any one example of 500 heads? The numbers are bigger, but the formula is still the same.
N to the power of 500.
We have the probability of heads to the 500 power
Multiply it by the
times the probability of tails
to
to
the 500.
the 500 power, right? That. Does that make sense? There it is. Okay, so if we want to conclude whether the coin is fair or not, we should not base our decisions on the probability of observing events like the one we observed, right? Because if we were doing that, we would say, oh my goodness, the probability of getting an event where you have 500 heads out of 1,000 flips is really low. So probably the coin's not fair. If you got this, even though the probability is low, probably that coin is fair, right? So this must not be a good decision rule, just figuring out the probability of events like the one that we saw. Well, this sucks. We've tried 2 different decision rules, and both of them have failed, right? What else is there? What else could we do? Maybe we could base our decision on the probability of events as or more extreme than what we observed. This is actually going to be what is going to work. This is going to be what we're going to do. So, not the probability of observing an event, not the probability of observing an event like the event we observed, but the probability of observing events like the one we observed, or more extreme than that. Okay? So, how are we going to do this? Well, we need to get the probability of events as or more extreme than what we observed. This is easy. We can calculate this very easily, right? For each type of event, as or more extreme, we just do what we did previously, right? Probability of heads raised to the number of heads, times the probability of tails raised to the number of tails, times the combination for that many heads in that many observations, right? So the probability for that event type is equal to the probability of any one event like that times the number of events total like that. Once we have the probabilities for each of these events that are like our event, as extreme as that event, or more extreme than that event, we just add all those probabilities up, right? Because again, these are mutually exclusive probabilities. So we just add them up. All right, so if we get 10 heads and 10 flips, there we go. Can you tell me the answer? What is this again? It's almost 0.001, right? We can figure it out. Now, are there any other types of events that are as extreme as getting 10 heads? Getting 10 tails, right? 10 tails is just as extreme as 10 heads if the probability of getting a heads and a tail are equal, right? So, 10 tails and 10 flips is just as extreme. I'm not going to write down tails, I'm going to stick with the heads, but I use 0 heads, right? Because 10 tails is just 0 heads. So the probability of 0 heads and 10 flips, well, what's this? Basically just flipping the numbers here, right? We'll have a 0 here instead of the 10, we'll have a 10 here instead of the 0. This will stay the same. We'll have a 0 here instead of the 10, and a 10 there instead of the 0. Boom! It's the same answer. So now we have the probability of events like the one that we saw, and the probability of events as extreme as that. probability of events more extreme than that, right? So what's more extreme than 10 heads in 10 flips? 11 heads in 10 flips would be more extreme, right? If you observed 11 heads in 10 flips. But what's the probability of that? 0. That's exactly right. The probability of that, I mean, we could say, okay, this p heads to the 11th times p tails to the 0 times this. I would not do that. But how many times would you observe it? You wouldn't observe it any times, right? I'm sure the math works out. I'm not a mathematician. I don't know what negative 1 factorial is. That's embarrassing. I don't know what negative 1 factorial is. I'm guessing it would be 0. I don't know. Whatever. Okay, so we add up the probabilities for the types of events as are more extreme than what we observe. So what is this? 0.001 plus 0.001. So the answer is 0.002, approximately, right? So that's that. Great. Seems like pretty convincing evidence that the coin is not fair. Is it? Well, if we now try looking at the most common event that we should see, let's see how it works out. So 5 heads in 10 flips. What types of events are as or more extreme than 5 heads? 5 heads is as extreme as 5 heads, right? Okay, so we've got that. We've got the 5 heads. What's more extreme than 5 heads?
All of them.
Basically anything, right? 6 is more extreme, 7 is more extreme, 4 is also more extreme. That would be like 6 tails, right? So all of those are more extreme. Now notice that this includes every event type. Every event type. So since we know that it includes every event type, what would the probability of observing events as or more extreme than this be?
1.
1, right? How do you know that?
Because we have the answer in the first section that all of them sum up add to 1.
That's right. The sum of all of the probabilities are going to equal 1. These events, if we were to draw a Venn diagram, right? We'd say like, okay, well the 4 heads, that's like this one, or 5 heads is like that much, the 4 heads, we could figure out how much of those are. That would completely fill the entire diagram, all of those events. So the probability is 1. Cool. Probability is 1 that you would observe an event as extreme or more than what we saw, right? Well, if the probability of observing an event like that, or more extreme than that, is 1, well, that's pretty good evidence that the coin is fair, right? Alternatively, when we saw we had the 10 heads in 10 flips, what was the probability? It wasn't 1. It was close to 0, right? So this value that we calculated, this is the p-value. So the p-value is the probability of observing an event as or more extreme than what you observed. The asterisk is here because we should put in given the null hypothesis. Right? For the most probable event types, for the events that you are most likely to see, like 5 heads out of 10 flips, the probability, or I'm sorry, not the probability, the p-value will equal 1. 500,000 heads in 1 million flips, the p-value would equal 1. For a fair coin. As the event types become less and less probable, p-value is going to approach 0. So p is what we're going to use to make our decision. The p-value, which is the probability of observing an event as or more extreme than what you would expect. Right? All right, so how low do we go? This is an interesting question. So when is the p-value low enough for us to conclude that the coin is not fair? You know, I said, imagine I flipped the coin 10 times, right? And it came up heads every single time. It was heads, yeah. It was heads. Ah, I blew it. So, 10 and 10, right? The p-value for that was 0.002. Is that low enough? Are you willing to say, yeah, the null hypothesis is probably wrong, coin is probably not fair? Well, let's go with an easier question.
For psychology?
We flip it once, right? And it turns up heads. Flipped it once and it turns up heads. What's the p-value for that? Not 0.5. 1. Right? So we said if it came up heads for one flip, we're not very convinced. Right? The p-value for 5 heads and 5 flips? Yeah, 5 heads and 5 flips.
That's not fair.
Here we go. Probability of 5 heads and 5 flips. So that's just the probability of the heads 5 times, right? So the p-value is what? Are there any events as extreme as 5 heads in 5 flips? What is it? No heads in 5 flips, right? And the probability of that would be?
0.62.
Would also be 0.031. So you add those together, and it'd be 0.062, right? So if you got 5 heads in 5 flips, the p-value for that is 0.062. Is that enough for you to say, okay, the coin is not fair? You want to flip more? Okay, so we do it 10 times, and we get the p-value of 0.002. Is that enough? Are you willing to conclude that the coin is not fair? You're shaking your head.
We can't conclude the coin is fair just by flipping it from using the. We need to go to the most probable event, which is having 5 flips by 10 times.
Right, but we didn't observe 5 flips in 10, or 5 heads in 10 flips. We observed 10 heads in 10 flips, right? So the probability of seeing events that were more extreme is really, really low. It's 0.002, approximately. Is that strong enough evidence for you to conclude? You say no. How much evidence do you want?
We can't conclude when it's all heads for all the, because we can't conclude that. We need that.
You can't conclude when it's all heads or all tails. So if you flip it 1,000,000 times and you get 1,000,000 heads, you can't conclude that it's. Who in here would be willing to conclude that the coin is unfair if you saw 1,000,000 heads and 1,000,000 flips?
Unfair or fair?
The coin is unfair.
Unfair. It's of course unfair.
Yeah, I would argue that the coin is unfair. So how low does that p-value need to be before you were willing to say that the coin is unfair?
We determine in psychology or other scientific field, in psychology is 0.05.
0.05. 0.05 is the point that psychologists are typically using as their cutoff for p-values. So, the traditional cutoff is 0.05. This would mean that after 10 flips, if we observe 10 heads, that is beneath 0.05. So, different disciplines, as I mentioned, have different criteria for what their cutoff is. The criterion that you set, this cutoff that you set, this is called alpha. At whatever value that you set it. If you set the cutoff at 0.1, well then your alpha is 0.1. If you set it at 0.001, then your alpha is 0.001. So alpha is just the cutoff that you pick for you to determine when you have enough evidence to conclude that the coin isn't fair, right? So some people, they say, well, 10 heads and 10 flips, I know that's improbable, but like, I want more evidence, right? What does that suggest if they want more evidence? Where are they setting alpha? Above or below 0.05? So alpha is the cutoff, right? When our p-value falls beneath that, then we're going to say, aha, the null hypothesis is unlikely. These results have a low probability of having occurred due to chance. But not just these results, but these results and results as or more extreme than these have a really low probability of occurring. Right? So if you aren't happy with the 0.05, and you want to see, let's say, 100 heads and 100 flips, is your alpha higher or lower?
No.
It's lower, right? So someone that wouldn't be convinced until you had 100 heads and 100 flips, their alpha would be really, really low, right? All right. Let's emphasize what we learned so far and define a couple more words. So back to our question, is the coin fair? So this is our research question. We have two alternatives, right? What are the possibilities? The coin is fair and the coin is not fair. These are hypotheses, right? Hypotheses are just statements about the way the world works, or something in the world works, or how an event occurs. Just some statement about your belief. So we need to pick a particular hypothesis to test, right? We have two alternative hypotheses, right? One is that the coin is fair, the other is that the coin is not fair. Which one should we test?
It's fair.
The one that says the coin is fair. Why? Let's see how well you guys picked up this time. So why? Why do we use the coin is fair?
We know the probabilities then. If it's not fair, it can be 0.7 or 6, but if it's fair,
Exactly.
it's 1.5.
So this hypothesis gives us a place to start. It says that the probability of heads is 0.5. Also says that the probability of tails is 0.5. This, it says that it's not 0.5. Okay, so what is it? We need that probability in order to compute the other probabilities, right? If we don't have a probability of heads or a probability of tails to start with, then we can't compute p-values, right? So we need that information. This one provides it. This one doesn't. So the null hypothesis is going to be the statement about the world, its objects or events that we're going to test. So in this example, the null hypothesis is that the coin is fair. So null means without value. It doesn't have a value. Most null hypotheses will include statements like there is no relationship between gender and political persuasion. There is no difference between test scores after studying with a deep level of processing versus a shallow level of processing, right? Or no effect. There's no effect of the depth of processing, right? Why? Why is this? It's exactly the reason that she said, which is that it provides values for the parameters that we need to calculate the probability, right? In order to calculate the probability, we need probability of the heads or the tails, if we know one, we know the other, right? So we need one of those probabilities. We need to know how many times we're flipping the coins. Once we have those, then we can calculate the p-value for any number of heads or tails that pop up, right? So, the null hypothesis is the coin is fair. This tells us that probability of heads is equal to 0.5. The coin is not fair? We have no idea. We don't have a starting point. Here's a statistical question that someone who's in the business world might be interested in. Imagine someone who's doing quality control and they want to make sure that Chamlaja's 1 liter bottles have 1 liter in them, right? Or maybe you're a lawyer, maybe you're a poor student and you want to make some money. So you're thinking you might want to sue Chamlaja. Don't sue Chamlaja. They're like my favorite soda. America is in serious need of some Chamlaja. Okay, so you want to make some money, right? So you could get a whole lot of bottles of Chamlaja, right? And then measure how much water or how much soda is in it, right? Now, the null hypothesis would be that 1 liter bottles of Chamlaja contain 1 liter of soda. This is interesting because we said null means no value, right? Or without value. But here we're actually predicting a value, right? It wouldn't make sense to say like Chamlaja bottles have no soda in them in it. Because they do. I mean, quite clearly they have soda in it. On the bottle it says 1 liter, right? So we could use that as the null. Let's see if they really have 1 liter or not, right? We could state it as a difference. There is no difference between what's actually in the bottles and what Chamlaja claims is in the bottles, right? So we have a value to start with, and that is liters in the bottles equal 1. The alternative hypothesis would be that 1 liter bottles of Chamlaja do not contain 1 liter of soda. In this case, we don't know what it is. Could be 1.01 liters, it could be 4 liters, it could be half a liter, we don't know. This provides us with the starting, provides us with the parameter. Okay, how can this be restated as a hypothesis of no difference? I explained how can this be a hypothesis of no difference? If the coin is fair, what 2 things are the same? Yeah, so if we wanted to restate this as a no difference type of hypothesis, we could say the probability of heads equals the probability of tails, right? All right, why do we test the null hypothesis instead of the alternative hypothesis? Well, extraordinary claims require extraordinary evidence. As I mentioned last class, people make non-null hypotheses all the time. You drink your pee, you'll live longer. You wear a magnet bracelet, your pains will go away, right? So if we assumed all of the things that people say are true, we would waste a lot of our money, right? So we test the null hypothesis to figure out, or to try to figure out, whether or not the claims that people are making are actually true. By setting up the cutoff for our p-value low, what this means is that we are requiring a lot of evidence before we are willing to conclude that the null hypothesis is probably wrong. So when people are saying 10 heads in 10 flips is not convincing enough for them, what they are saying is that they want extraordinary evidence. They want much, much more solid, much, much stronger evidence that the null hypothesis is false, right? Okay, so our decision rule. Our decision rule is when p is less than or equal to alpha, we're going to reject the null hypothesis. When we reject the null hypothesis, we can refer to the results of the test as statistically significant. When the probability is greater than alpha, we fail to reject the null hypothesis, and we refer to the results of the test as statistically non-significant. No, we're testing the null hypothesis, right? We're taking the parameters that we get from the null hypothesis. So we're not really testing the alternative hypothesis, we're testing the null hypothesis, right? So when we are saying what we're doing, we should keep them in terms of the null hypotheses. We reject the null hypothesis. We fail to reject the null hypothesis. Not we reject the alternative hypothesis, right? Because we're not testing the alternative hypothesis. We are testing the null hypothesis. All right, so let's make some better definitions for P and A. So P is the p-value, the probability of observing results as or more extreme than what we observed if the null hypothesis was true. So this last part just fills in that asterisk that I had before, right? Because the null hypothesis gives us those parameters. If we didn't have them, we couldn't compute the p-value. This is an inferential statistic. So the number of observations that we had that turned up heads, that's a descriptive statistic. The p-value based on that descriptive statistic is an inferential statistic. It allows us to draw inferences, right? We have enough evidence to conclude that the coin is fair. But we did not have enough evidence to conclude that the coin is fair, right? Alpha is the minimum p-value required to reject the null hypothesis. This is basically very close to the way I described it. But we can also think of it as the probability of incorrectly rejecting the null hypothesis, right? How does this work? Well, I said, if the coin is fair, we should observe 10 heads in 10 flips. Like that would be 0.1% of the time, right? Is the probability. This is basically just 0.1%. So we would expect to observe. Are you missing me? Do you get that?
Yeah.
Okay. We just multiply the probability times 100 to get to percent, right? So even if the coin is fair, we're going to observe 10 heads and 10 flips on 0.1% of the time, right? So if we set our alpha to be 0.05, this means that we are rejecting events that have a probability, or not, we are rejecting events whose p-value is less than 0.05. So the probability of events that are more extreme. Now notice, you can still observe those events, right? With the fair coin, you can still observe those events with whatever the probability that they are. So by setting the alpha at 0.05, what you are doing is you are going to incorrectly reject the null 5% of the time when the null actually is true, just by the way you set it up. So alpha, in addition to thinking about it as being the minimum p-value required to reject the null hypothesis, is also the probability of incorrectly rejecting the null. Because we're wrong sometimes. This is why I don't like proof, right? So the general process of statistical testing is to state the null hypothesis. We're going to set our alpha. We are going to determine our sample size. We are going to collect our data. Then we're going to calculate p, right? We can calculate p because we have the parameters provided by the null hypothesis and our sample size. We also have the descriptive statistics provided by our data collection. Once we calculate p, we make our decision. We reject the null hypothesis if p is less than or equal to alpha, and fail to reject otherwise. You need to do these in order. It's important. There are some people that don't set alpha until after they've already calculated p. What would the problem with that be?
You might be biased towards your results.
Yeah, if I know what the p-value is, right, then I can set alpha to be just a little bit above that. Oh, look! It's significant! Right? So we need to set alpha first. Also, we need to determine our sample size first. Because there are some people, this is not a good way to do research. Like, they'll flip coins, or not flip coins, but they'll do a real research problem, and they'll collect their evidence, and then they'll calculate the p-values. They'll say, is it less than alpha? Or, no, okay, it's not. All right, let's collect a couple more people. No, is it less than alpha? Oh, no, it's not. Okay, let's collect a couple more people. Is it less than alpha? Yes, it is! This is a bad way to do it, because what you are doing, if you do it that way, you are capitalizing on chance. Because sometimes things that are unlikely. So by waiting until you just happen to get an unlikely set, you're capitalizing on chance, and your alpha would actually be much higher than what you say that it is. There's a video of someone on YouTube flipping coins, and they do 10 in a row. They flip the coin correctly, or heads up 10 times in a row. It's a really wimpy flip. It's like, and it goes into a bowl so it doesn't like go all around. So it basically just turns once, and then that's it. Anyway, if you watch the unedited version of this, it's like hours long. So the person, he has a timer set up, and each time he gets a heads, he says, it's heads. Oh, it's 2 heads. And then usually he'll get a tail. So then the next time he gets a heads, it's 1 heads. So he basically just did this again and again and again until he got 10 heads and then edited it together, right? It said, oh, look. So you need to determine your sample size before you run the experiment. So back to our point. If the null hypothesis is that the coin is fair, we know the probability of heads equals 0.5. Alpha, we're going to set it at 0.05. Say we have a sample size 10. Those are the parameters we need to calculate P. We observe 8 heads. That's the statistic that we need to calculate P. And there's the calculation that we need, right? The probability of getting 8 heads plus the probability of 2 heads, which is as extreme. Plus the probability of 9 heads, which is more extreme, plus the probability of 1 heads, which is also more extreme, plus the probability of 10 heads, which is more extreme, plus the probability of 0 heads, which is also more extreme. So the probability of getting 8 heads in 10 flips is approximately 0.11. What do we do? I take this. We compare it not to the B value. You said B value? We don't have a B value up here yet.
To the A.
We compare to the A, right? So we compare P to alpha. All right, is P bigger than alpha, smaller than alpha, equal to alpha?
No,
P is bigger than alpha. What do? We fail to reject the null hypothesis, right? There is insufficient evidence to conclude that the coin is not fair at that level of alpha. A different coin we do it. The coin is fair, probability of heads is 0.5, we've got our alpha 0.5, we do a sample size 10 again. Got the parameters we need to calculate P, we observe 1 head, that's the statistic we need to calculate P. What's that probability? It's just that. It's approximately 0.02. So, what do? We reject the null hypothesis. Why?
less than.
Because P here is less than alpha. And we said when it's equal to or less than alpha, we're going to reject. So we reject the null hypothesis, and we conclude that there is sufficient evidence to conclude that the coin is not fair. Okay, so what do we call the test that we just did? It's the bodacious binomial test. Or if you're not as excited as I am, you can just call it the binomial test. Now, when can you use it? You can use it whenever you have 2 complementary outcomes. Heads, tails. These are 2 complementary outcomes. If you don't include people with atypical chromosome patterns, you can say male, female, right? You can say Muslim, non-Muslim. You can say psychology, not psychology. You can say lots and lots of things, right? Whenever you have 2 complementary outcomes, or whenever you can organize outcomes into 2 complementary events. So if we're going to roll a die, we have 6 potential outcomes, right? But we can organize them into a 6 or not 6s, or even odd, right? They're both complementary. Why the binomial is so bodacious? The binomial calculates exact probabilities, right? We have a formula. We were able to calculate exactly probabilities for things. So no estimation is required in many cases. This is not going to be true of a lot of the other statistics that we're going to talk about. Many research questions can be reframed for the binomial test, which is often not a great idea because you often are throwing away data when you break it down into just 2 things. But you can do this in a pinch if you don't remember what the other tests are, which is why if you're going to remember one type of test from this class, I am hoping that it will be the binomial. So, is your teacher biased? Am I biased? Is some other teacher biased? Right? If I am not biased, then I should have an equal probability of calling on a female as the probability of females in this room, right? So, today we've got, I guess like 95% females. Gibby? 90-something% females, right? So, we have 90-some% females. This should mean that if I'm just randomly calling on people, right, not answering a question, because sometimes I'll ask a question and someone will answer, but if I just pick someone, okay, close there. Okay. Come here, I want to call you the wrong name. Watasa. Right? I should call on women. The probability of me calling on women should be the same as the probability of just randomly picking a woman. Right? So, imagine that there are 30 females and 10 males. The null hypothesis would be that the teacher isn't biased. Right? Probability of calling on a female for this should be 75%. Right? There are 30 females, there are 40 total students. It's 3/4, just 0.75. Right? Alpha, okay, it's 0.05. Say sample size is 200. So you sit in my classes with 40 students with that distribution, and you mark off every time I call on someone, and you indicate whether it's a male or a female. So, okay, female, 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 male, female, female, male, female, female. You're doing this, right? Wait till you get 200. And then you see that I called on women 137 times. Oh. Probability of observing an event that or more extreme is 0.041. What do you do? It's less than alpha. You reject the null. There is sufficient evidence to conclude that your teacher is biased. Is there 1 liter of soda in chocolate? There's 1 liter bottles. Imagine we're measuring so precisely that we never ever observe 1 liter. Okay, so we're like measuring down to like milliliters or nanoliters or something. So like we're never gonna get exactly 1 liter. Now the null hypothesis would be that the label is right. Right? There's 1 liter of soda in the 1 liter bottles. So that means the probability of less than 1 liter is 0.5. Probability of more than 1 liter is 0.5, right? Alpha is 0.05, our sample size is 1,000. We really, really like Chamla-Jaw. And we find that Chamla-Jaw has less than 1 liter of Chamla-Jaw in it 473 times. So, do our calculations. The p-value is 0.094. This is more than alpha. What do? We fail to reject. There is insufficient evidence to conclude that Chamla-Jaw's 1 liter bottles contain less than 1 liter of soda. It's funny. This is like sort of a silly kind of example, but in industry, these types of questions are really important. Businesses do these types of tests all the time to make sure that they are putting out a consistent product, that their product is matching their standards. We don't need influential statistics to evaluate all hypotheses. So all swans are white, no swans are black, some swans are white. All we need is one observation to prove or disprove. Right? Here we can talk about proof or disprove. Can we prove that all swans are white? We can't prove that all swans are white. Can we disprove it?
No.
Yes, we can.
We can disprove it. We can't prove it because we can't observe every part of space at every point in time, right? So because we can't observe everything, we're not sure if there's really a black swan out there, right? But if we observe one black swan, what do we know? We know that that's false. How about this? Those swans are black. Can we prove that? says yes. Can you prove that no swans are black?
No.
Again, you can't prove this because you'd have to look everywhere, right? Can you disprove this? Yeah, you can. I mean, this is basically the same thing. All swans are white, no swans are black, right? So again, we can't prove it, but we can disprove it. How about some swans are white? Can we prove this?
Yes.
Yeah, all we need to do is find one swan that's white and we met the criteria. We can't disprove it, right? For these, we don't need inferential statistics. We just need one descriptive statistic. Aha, we saw one. So you might need lots of time and patience for things like these. Like some biologists are interested in questions like these. Are panda bears extinct? Well, not panda bears maybe, because we know that they're not yet, but maybe is some other type of animal extinct? Right? All you have to do is find one that's living to say, oh, no, they're not extinct yet. We're not going to spend any more time on these types of hypotheses. We're going to do the more interesting hypotheses where there's lots of chance and variation involved. A final thought about alpha. So one definition was the probability of incorrectly rejecting the null hypothesis, right? So we said with alpha of 0.05, how often are we incorrectly rejecting the null? What percent of the time are we incorrectly rejecting the null when alpha is 0.05? Not 50%. So the question was, what percent of the time do we incorrectly reject the null when we set alpha to 0.05? So alpha of 0.05 means that, yeah, 5%. When alpha is 0.05, we are incorrectly rejecting the null 5% of the time, right? We're assuming the null hypothesis. We're calculating values based on the null hypothesis. And we say when those probabilities are small enough. Notice not when those probabilities are 0, but when those probabilities are small enough, we're going to reject the null. So even though those events are improbable, they sometimes happen, right? So this means that we are making some mistakes. If alpha is 0.05, we will incorrectly reject the null hypothesis 5% of the times. This means that many conclusions based off of statistically significant results are wrong, right? So when I flip the coin 10 times, and I get 10 heads, you guys know, you're like, well, it could be not fair, but it also might have just been an accident, right? It still could have just been due to chance, right? That's that alpha error. So this is why it's so important to replicate results. If one person finds a relationship between two variables, it's important for someone else to see if they can also find a relationship between those two variables, right? This is why you should be skeptical about any published result. So, like 2 years ago, someone published this paper that basically showed extrasensory perception, that people could tell the future. It has not been able to be replicated. Lots and lots and lots of people have tried to replicate the results. They've failed. Which suggests what? Suggests that they made an error. Those results actually, the results were what the results were. But probably the null hypothesis was correct, but it was incorrectly rejected. Right? This is especially important if you can only find one publication with some result. So some people, they have to write a paper, and they want to provide some evidence for something that they're saying. So they look, oh, can I find any article that says this? If you can just find one article that's not really good evidence, what you want are a couple articles finding the same result. If you have just one, it could just be that you have this type of error. Journals usually don't publish null results. That is, when you don't reject the null hypothesis, when you fail to reject it. So what this creates is a file drawer effect. There are lots and lots of experiments with null results, but they aren't reported in the literature. Which means that you're only seeing a tiny portion of the results that are out there. So if you don't see a number of results converging on the same answer, you need to be skeptical. All right. Next class, we'll talk about power, peptides, alpha and beta errors,